Hello everyone, welcome to my class. Today I'm going to cover triple integrals. In our previous classes, we defined a double integrals for a function of two variables. So the double integrals template in Cartesian coordinate is double integrals of f of xy, and we integrate with respect to the area element dA over two dimensions region D, where dA is either dx times dy or dy times dx. Similarly, we define double integrals over polar regions. The double integral template in polar region is, or polar coordinate is, double integrals of f of r cosine theta, r sine theta over a polar region R, and we integrate with respect to area element in polar coordinate. The area element is simply r dr d theta. And today we are going to define a triple integrals for a function of three variables by much the same procedure that we use for the double integrals. So the triple integrals template is triple integrals of f of x, y, z, and we're integrating with respect to the volume element dV over a three dimensions boundary region E. Since the volume element dV has these six many possible orders, so we have six many possible orders of integrations of triple integrals. So for example, if I pick dv equals to dz dy dx, then my triple integrals can be rewritten as triple integrals of f of x, y, z over E with respect to dv, your volume element, equals to x integrals, y integrals, z integrals of f of x, y, z, dv equals to dz dy dx, and this dz is for this z integrals, and this dy is for y integrals, and dx is for x integrals. So here I refer in my lecture below, z is my inner variables, y is my middle variables, and x is my outer variable. Then corresponding their integrals, z is the inner integrals, y is my middle integrals, and x is my outer integrals. So great. Let's move on. In this special case, if our three-dimensional boundary region is simply a rectangular box with side AB cross CD cross EF, then our triple integrals of f of x, y, z dv over E can be written as an iterated integrals f of x, y, z dz dy dx, and z integrals with a z bound, z equals to E to f, y integrals with y bounds, y equals to c to d, and x integrals with x bounds, x equals to a to b. Great. Special case, if f is a constant one functions, then we interpret the triple integral as a volume integrals. So the volume using triple integral is the formula v equals to triple integrals of 1 dv. So quick example, compute the volume of the rectangular prism with side 04 cross 01 cross 03 is v equals to, integrand function is 1, dv equals to dz dy dx, and z integrals with z bounds 0 to 3, y integrals with y bounds 0 to 1, and x integrals with x bound 0 to 4. Since integrand function is 1, so to compute the integral we simply multiply the upper limits. So 4 times 1 times 3, which is 12. Great. Now let's move on. Now in general, here's the tricky part in triple integrals. In general, it's not obvious to determine the limits of triple integrations. So at this moment, we can ask the questions to ourselves how to set up a triple integrals. So let me explain an idea. Now I'm picking in order my dv equals to dz dy dx, then I'll give you an example. an idea. So here dv equals to dz dy dx. So first of all, I want to find out the limits for z integrals, because z integral is my inner integral in this order. And then next, after I found the z bounds or z limits or limits for z integrals, then the triple integrals reduces to the double integrals. I am finding the bounds for y and x, which is the double integrals, which we already knew. So we use the idea of our last sections. Great. So let's move on. Let me scroll down. So first I would like to sketch two diagrams. One, a three-dimensional solid region E, and describe the region E as a z-simple and find the boundary of z variables, which are the surfaces. And then this xy is coming from the plane region D, which I define in second step here, which is simply the projection of E on xy plane. Let me go over this first idea. Then after we found the z bounds for the z integrals, then we can rewrite our triple integral as triple integral of f of xyz dv equals to f of xyz and dz is my z is my inner variables, or z integrals is my inner integrals. Then the left is double integrals over x and y, and xy is coming from d. Then I go to the part second, where d is a projection of E on xy plane. Then we have two choices to find the limits of x and y in plane region D. Either we can use D as in a rectangular coordinate systems or in a polar coordinate systems. If it's a polar coordinate systems, then we find the limits in terms of r and theta. If we choose rectangular coordinate system to describe our plane regions D, then again we have two choices. Either we can describe our plane region D as y simple, that is vertically simple, or horizontally simple, or x simple. So if I pick y simple, then my domain D in R2 or in xy plane, which is bounded by two continuous functions top and bottom, and on the side is bounded by a fixed value of x. Then, as shown in these diagrams, I pick a vertical slice. Then I pick a value as an entering value, and then the exiting value given by the function of x for y. So y bounds are g1x to g2x, and for x equals to a and v for the x values, or the x limits or x bounds. Then our triple integral reduces to triple integral of f of xyz dv over E equals to f of xyz, and then I pick dv equals to dz dy dx order. Then my inner integral is with respect to z, or z integrals, whose bounds are the two surfaces, top surface h to xy and bottom surface h on xy, where this z limits of these z integrals depends on middle variables and outer variables x and y. And in the next is the middle integrals, which is the y integrals, whose limits are g1x to g2x. So in other words, the limits of y integrals depends on outer variables, x variables. And then the last one is the outer integral, which is the x integrals, whose limits must be constant. So one more time, so the triple integrals of f of x, y, z with respect to volume element dv over E equals to triple integrals of f x, y, z in dz, dy, dx order. Inner integral is z integrals, and then the middle integral is y integrals, and then the outer integral is x integrals. And the z integrals can depend on these two variables x and y, and the y integrals can depend on the x variables, but x integrals must have a constant bounds or constant limits. Hopefully this idea makes sense to you how to set up a triple integral in this particular order, dv equals to dz dy dx. One more small comment: if you change the order of integrations here, then your limit also changes, but keep in mind our integrand functions f stays the same. Great. Now let's move on. Now we have a triple integrals template. Now let's solve some examples. Let's start example 1. Evaluate a triple integrals. Triple integral is given as I equals to outer integrals going from 0 to 2, middle integrals going from 0 to z square, inner integrals from 0 to y minus z of 2x minus y times dx times dy times dz. So that means our x integral is the inner integrals in this particular example, y integral is our middle integrals, and z integral is our outer integrals. So great. So let's start the solutions. Write down the z integrals and y integrals and integrate the 2x minus y with respect to inner variable dx. So keep in mind, when you are integrating with respect to x, y is constant. So the integral of 2x becomes x squared. Integral of y with respect to dx becomes yx, and put x limit x equals to 0 to y minus z and dz, dy dz. Next, write down z integrals and y integrals. Oh, this z is squared here. It's a typo. And then put x equals to upper limit y minus z. So y minus z squared minus y minus z times y dy dz. Write down z integrals, write down y integrals, and simplify these expressions, which gives you z squared minus yz times dy dz. Now we are integrating with respect to y, so z squared is constant. So in the next step, write down z integrals. Then the integration of z squared with respect to dy is simply y times z squared minus integrations of yz with respect to y is y squared over 2 times z, and then put the y limits y equals to 0 to z squared dz. Next step, write down z integrals and put on these expressions, put y equals to upper limit z squared and simplify, and subtract y equals to lower limit 0, simplify, which is 0. So simply we got when y equals to z square, then we got our last integrals, z to the power 4 minus z to the power 5 over 2 dz. Then integrate this last integral with respect to dz, so z to the power 4 becomes z to the power 5 over 5 minus z to the power 5 over 2 becomes z to the power 6 over 12. Put z limits. Put z equals to upper limit 2 and simplify. This gives you 16 over 15, as z equals to 0, lower limit gives you all 0. So we found the value of this triple integral as 16 over 15. Great. Let's move on. Example 2. Evaluate the triple integrals of 6xy over e dv, where e lies under the plane given by z equals to 1 plus x plus y, and above the region in xy plane, bounded by the planes y equals to radical x, y equals to 0, and x equals to 1. Great. So let's start the solutions. So let me pick dv equals to dz dy dx order. dz dy dx order. So first find the limits of g, and then find the limits of y, and then x. So to find the limit of g, find the boundary of g between two surfaces. So here, so g equals to 1 plus x plus y is a top surface, and then the bottom surface is xy plane where z is 0. So in first we found g limits between 0 and 1 plus x plus y. Great. And then to find the xy limit of x and limit of y for the double integrals, let's sketch the plane regions, which is given by y equals to radical x, this curve, y equals to 0, x-axis, and x equals to 1, this vertical line. So our plane region is the shaded area here. So then describe this plane region D as y simple or vertically simple, then draw a slice. Then we found the lower limit of y given by the x-axis and upper limit of y, or the upper bound of y given by this y equals to radical x. So we found the y bound 0 to radical x, and for the x bound we found x equals to 0 to x equals to 1, so x equals to 0 to 1. Great. Now for these triple integrals we have the limits for g and x and y, or the bounds of x, y, and z. Great. Now let's start with the given triple integral. So I equals to 6xy. I pick the order dv equals to dz dy dx. So the inner integral is with respect to z, so the z with z bounds 0 to 1 plus x plus y square. And then middle integral is y integrals with y limits, y equals to 0 to radical x. And then the outer integral is x integrals whose limits must be constant. Here x equals 0 and 1 both are constant. I hope this setup makes sense to you all. Now let's do the integrations. Let's compute the integrations. Write down the x integrals, write down the y integrals, then integrate with respect to dz. 6xy is constant for z integrals, so pull the 6xy outside, then integration of dz is z equals to upper limit 1 plus x plus y times dy dx equals to, write down x integrals, write down y integrals, then FOIL 6xy times 1 plus 6xy times x plus 6xy times y dy dx. Next, integrate with respect to y. Keep in mind x is constant for y integral, so write down x integrals, then the integration of 6xy with respect to y becomes 6xy square over 2. The 2 and 6 cancels 3 times, so 3xy square, the first term. Similarly, second term becomes 3x square y square, third term becomes 2xy cubed, and put y equals to 0 and radical x times dx. Next, equals to, write down x integrals and put y equals to upper limit radical x and simplify. This gives you this expressions: integration over x equals to 0 to 1 of 3x square plus 3x cubed plus 2x to the power 5 half dx. Note that when you put y equals to 0 and this expression disappears, becomes 0. Great. And integrate now the last integral with respect to x, gives you x cubed plus 3/4 x to the 4 plus 4/7 x to the power 7 half. Put x limits, x equals 0 to 1. Put x equals to upper limit to 1 in this expression and simplify. It gives you 5 over 28. So we found the value of this given triple integral as 5 over 28. Awesome. Let's move on. Excuse me. Now let's do example 3. Slightly different. Use the triple integrals to find the volume of the tetrahedron enclosed by the planes given by 3x plus 2y plus z equals to 6 and the coordinate planes. So our tetrahedron is bounded between this given plane 3x plus 2y plus z equals to 6 and the coordinate planes. So let's sketch the surface here. So let's find the cross section of this coordinate plane and with this plane. So put yz 0, then x equals to 2 is a x-intercept. Put xy 0, z equals to 6 is your z-intercept. Put xz equals to 0, x0, z0, then y equals to 3, then y equals 3 is your y-intercept. And in this surface, let's first find the bounds for z variable. So for the z variable, z equals to 0 is your lower boundary, and then the upper boundary is given by this plane or this surface, z equals to 6 minus 3x minus 2y. So now we found the z bounds. Now to find the x bounds and y bounds, project the surface on xy plane. Put z equals to 0, then we got 3x plus 2y equals to 6, which is this line. So then this bounds this region, the plane region D, which is a triangular region. Then describe this triangular region D as vertically simple or y simple, and draw a vertical slice, and we enter this region at x-axis. So for the lower bound of y is 0, limits are here, y equals to 0 is your lower bound, and for the upper bound is given by this line. This line equation is 3x plus 2y equals to 6, and solve for y, which is 3 minus 3 half x, which is here. Next, for the x bound, pick x equals to 0 and x equals to 2. Great, now we have the limits for x integrals, y integrals, z integrals. Then let's use a triple integrals to compute the volume. Our formula is volume equals to triple integrals of 1 dv. Then pick dv equals to, in this order, dz, dy, dx. Then inner integral is z integral with z bounds 0 to 6 minus 3x minus 2y. Then middle integral is y integrals with y bounds, y equals to 0 to 3 minus 3 half x. And then the outer integral is x integrals with x bound, x equals to 0 to 2. 0 to 2. Great. Let's integrate first with respect to z. So the dz becomes a z equals to upper limits. So write down x integrals, write down the y integrals of, then 6 minus 3x minus 2y comes from the dz integral, or dz integral, z integral, times dy dx. Great, let's move on. Next, let's integrate with respect to y. So write down x integrals. 6 becomes 6y, minus 3x becomes minus 3xy, minus 2y becomes minus 2y squared over 2 to cancel, simply minus y squared, and put y limits, y equals to 0 to 3 minus 3 half x times dx equals to, write x integrals, and then put the y equals to upper limit as lower limit equals to 0, so all terms 0, so just put y equals to upper limit and simplify. It gives you x integral 0 to 2 of 9 minus 9x minus 9/4 x squared dx. Then the last integral is integrated with respect to x, and put the x limits, x equals 0 to 2, and simplify. We got 6. So we found the volume of this tetrahedron using triple integral as 6. Great. Let's move on. Now example 4. Let me scroll down. That's better. Oh, that's better. Example 4. Evaluate a triple integral of x dv over E, where E is the regions bounded by paraboloid x equals to 4 times y square plus z square, and the plane x equals to 4. So again, in these questions, I'm not picking the order that we picked in our previous example. Now I'm picking a different order. So I'm picking dv equals to dx, dy, dz order. So in this order, then x integral will be my inner integral. So let's first find the bounds for x, and then for y and z is a double integrals. We'll find out by using the projection idea. So first x bounds. Let me sketch the surface here. So our surface is, this yellow region is a paraboloid and x equals to 4 is a plane. So first, for the x limits are bounded between this paraboloid and x equals to 4. So the lower bound of x is 4 times y square plus z square, and upper bound is 4. Keep in mind that this paraboloid is passes through origin, so this is obviously lower bound for x. And then for the y bounds and z bounds, for y integral and z integral, find the cross section of these two surfaces and project onto yz plane. So to find the cross section, solve these two equations, put x equals to 4 and solve this equation. So 4 equals to 4 times y square plus z square, cancels 4 on both sides. Then this reduces to y square plus z square equals to 1, which is a circle in yz plane. So it's a circle. Now I'm going to use a polar coordinate to find the limits for our double integrals. So in polar coordinate, put y equals to r cosine theta, z equals to r sine theta in yz plane. Then our area element will be r dr d theta, and we can replace y square plus z square by r square. And for the circle, our bounds are 0 to 1 because 1 is the radius of the circle, and for the theta it goes from 0 to 2 pi. Awesome. Now let's rewrite our given triple integral with those limits. So I equals to x and then dx and dv. That means dv equals to dx dy dz, dy dz equals to r dr d theta. So dv equals to dx times r dr d theta, and then x as it is, and then the x integrals will be my inner integrals, and then r integrals middle integrals, and theta integrals is outer integrals. Let's integrate first with respect to x. So write down, let me scroll down. Now the next step, write down theta integrals, write down r integrals, then integral of x becomes x square over 2, write x bounds, x equals to 4 times y square plus z square to 4 r dr d theta, equals to, write down theta integrals, write down r integrals, then put x equals to upper limit minus x equals to lower limit and simplify. This gives you this integrand functions, which is 8 minus 8 times y square plus z square, outside is square, and then write down r times dr d theta as it is. And now we know in polar coordinate y square plus z square is r square, which you found here. Now substitute here. So then this becomes r square r to the power 4. Next step, write down theta integrals, write down r integrals, then simplify this in polar coordinate, which is 8 minus 8 r to the power 4 times r dr d theta. Great. Now we can separate theta integrals and r integrals, and in the r integrals we multiply this r inside. So from theta integral it gives us 2 pi, and from r integrals, the integrals of 8r becomes 4r square, integrations of minus 8r to the 5 becomes 4/3 r to the power 6, and put r limits, r equals 0 to 1. And now put r equals to upper limit 1 and simplify. This gives us 16/3 pi. Awesome. So we found the solution or the value of this triple integrals, which is 16/3 pi. So great. So we finished these sections. In the next sections we'll cover triple integral and cylindrical coordinates. Thank you.